Hey, year 12. Thanks for coming along. Hi, Julian. Glad to see you there. Still waiting on Winkit and Dixon. Just wonder how long it... there we go. Let's see how long it takes them to appear. I'm going to be going through the second half of the June 2018 paper. I think that's correct. I'm just going to quickly scroll up on my tablet. I think that's correct. Yeah, this is June 2018, paper 2. It's an hour and 30. I've done an hour already, so I should be done in about 30 minutes. Multiple choice was relatively straightforward. And then we're starting with the equilibrium question. Oh, hey, Winkert, thanks for coming along. Great to see you. Still no Dixon. See how long it takes him. I'll crack on in a minute or so. Just having myself a little cup of Mesa. How are you guys? Are you guys all well? Okay, right. I'm going to crack on. Oh, good. Glad to hear it, Winkit. I'm going to crack on with the paper. I'm going to mark him as missing. That's what I'm going to do. And then I'll change that if need be. Right, let's do share screen and we can crack on with the paper. Now, I know that I did the first half, guys. I did the first half of this paper with the other year 12 class. So obviously worthwhile kind of for you guys to go back and watch the first one. But as I said, hopefully it will be done in about 30 minutes or so. We'll see how long it takes us to finish off the paper 2. And then we'll start the paper 3. The paper 3 is the interesting one. Paper 1 and 2 are relatively straightforward. So this question drops us straight in at equilibrium. The gas nitrogen, you have to know about this gas, by the way, folks. NO2, you guys have got to know is brown. You've got to be able to recognize it. From group 7 redox, that's where it appears. And dinitrogen tetroxide form an equilibrium mixture at room temperature. A gas syringe containing an equilibrium mixture of the gases is compressed by pushing the plunger and then allowed to stand with the plunger in the new position. Predict how the appearance of the mixture will change during this procedure. Yeah, okay, so this is quite a nice one. I've actually, I attempted to do this in class and failed because my gas syringes weren't good enough. But there are lots of great videos for this. So it's just nice to draw this out. So what does this actually look like? They've got their gas syringe, yeah, which has been corked. Yeah, and it's filled with a mixture of the brown gas, and we're going to get like, it's going to be coming like this. A brown gas and the colorless gas. So this is a mixture of NO2, which is brown, and N2O4, which is colorless. Now, what they're saying they're going to do is they're going to push the plunger in. Yeah, they're going to push it right down so it occupies a smaller space. So there's going to be this is going to have a stepwise change through it. Hey, Ange, nice to see you. Ange is one of my year 11s. You're gonna attend my AS paper 2 review. It's nice, actually, Ange. This particular question is right up your street. You can do this being year 11. So this is equilibrium, Ange. And we're just talking about a particular demonstration of equilibrium in gases. And I think I actually taught you this as well, Anch, when we did equilibrium at GCSE. So if you take that particular diagram and you take that gas, and you take the gas, this is still capped. Coughs, that's correct. Running coughs, spot on. And we push the plunger in so that the gas occupies, so this is the start. Yeah, this is the start. And then they push the plunger down. And I wonder how many of you will be able to guess what the very first, I have to go for maths, bye. See you later, Ant. What's going to happen to the color when this first, this is the pushers plunge down, yeah, and this is, hey, Dixon, glad to see you here. I'll add you to the register, Dixon, now that you're here. So the first thing that's going to happen, any ideas on the chat? What's going to happen at the very beginning? This is going to be as soon as the plunger is pushed down. Yeah, as soon as the plunger is pushed down, the color's going to change. Yeah. And it actually has a two-step process. So the first thing that's going to happen, this is where I need to be able to alter my colors. The first thing that's going to happen is it's going to get darker. And the reason for that is because all of this brown color, all of the brown NO2, yeah, which is spread out over this area, is going to be pushed into a much smaller volume. So the concentration of NO increases, so it will darken. So the first thing that's going to happen is we're going to see it darken. Yeah, but then we wait for the equilibrium to be established. Yeah, there's going to be a pause here. So this is stage 1, this is stage 2, and then in stage 3, I'll draw this. Stage 3, something rather curious happens. This was first observed by a very famous chemist called Le Chatelier, French chemist who was obsessed with gases. And what then happens is, after stage 3, after a few minutes, it changes color again. Yeah, it actually returns, it actually becomes this again. So it's a rather fascinating, so it says, predict how the appearance of the mixture would change. So the first one is, it will darken, and then lighten. Yeah, that's what's going to happen. And they want, and justify your answer. Yeah, so it darkens due to brown NO2 being in smaller space. If you run off the end, by the way I've just done, they won't be able to actually mark it. Being in smaller space, it then lightens as equilibrium shifts to reduce pressure. Reduce pressure. Reduce pressure, shifting from left to right. Reduce pressure, shift left to right. Left to right. Towards the less gas. I like it. Next, state and explain the effect of an increase in temperature on this equilibrium. Right. So we have to now, and this is 1 mark, annoyingly. Yeah. It's a bit of a nightmare. I don't know what they want. I'm just going to write them all. So the knowledge, we're doing temperature now. So the knowledge comes from my equation. Yeah. So this is exothermic. I'll be good as if I'm in an exam. Reaction is exothermic in forward reaction, in forward direction. Reaction is exothermic in forward direction. Forward direction. Next, oppose. If we raise temperature, equilibrium, then equilibrium will reduce temperature. That is one of the most lost marks in the whole of A-level AS chemistry and A-level just in general. If we raise temperature, then equilibrium reduces temperature, because most students reduce temp. Most students will write, the equilibrium opposes the change. You can't do that. You will lose that mark. Next, favors. Equilibrium. So how is it going to reduce the temp? Equilibrium will favor, we need the cold reaction, favor endothermic reaction. Thermic reaction, shift. Therefore, it's going to favor the endo, which is that one. That one's the endo. So it's going to shift from right to left. Shift right to left. Right to left. Yield decreases. Yield decrease. No idea what they wanted there for 1 mark. State and explain the effect of an increase in temperature. They don't want all of it. It's an absolute nightmare. Absolute nightmare, that is, folks. Absolute nightmare. Right, next. When potassium dichromate, oh yeah, they always like this one. Sorry, I'm just finishing off the register. There we go. When potassium dichromate is dissolved in water, the equilibrium is set up. The position of the equilibrium is well to the left of the solution is the orange color. Aqueous alkali is added and the solution turns yellow. Explain the results. Hey, coughs. I like it. Right, so what's the alkali going to do? Knowledge. Yeah, the alkali is going to remove H+. Knowledge. Alkali will react and remove H+ from mixture. Right, oppose. H+ concentration, therefore decreases. Equilibrium will shift to raise, to increase H+. H+ concentration. Move my F. Favor. By favoring, I want to make more of that. By favoring the forward reaction. Shift. S is shift. Shift from left to right. Solution turns yellow. We're done. Nice. Clever. Dead easy. Yeah, coughs just works brilliantly to run this. Yeah, there we go. This question is about the reaction and properties of 1-bromobutane. 1-bromobutane can be converted into 1-butan-1-ol in a one-step reaction. State the reagents and conditions required for this. Right, so we want to go from bromo to ol. Right, nucleophilic substitutions. The reagents is sodium hydroxide aqueous. Sodium hydroxide is the reagent. That's actually it. Don't need anything else. Yeah. It's interesting that they say reagents. Okay. Reagents that matter. Conditions are warm, aqueous, dilute. Those are the conditions. WAD, that's how I remember it. Yeah. If you want to do another way of remembering that, yeah, ORD, I don't know. DAO, don't know. WAD, I don't know. WAD. Mechanism, nice and easy. 1-bromobutane, this is nice and straightforward. A single step reaction, dead easy. Yeah, make it nice and clear for them, show all bonds, yeah, all atoms. I had a student once who forgot to show every hydrogen on all his organics. Very upsetting. Right, so delta positive, delta negative. First step, find your deltas. Next, put on your nucleophile. So OH minus should be on the O, lone pair shown. Right. Curly arrow number 1, curly arrow number 2. There we go. Product. That's actually the mechanism is all over at that point, folks, just so you know. That's it. It's 4 marks. Wow. Don't know how that can be 4 marks. Will charges in place? Fine. That's it. Explain why. I feel like I want to show a product or something. It'd be fascinating to see where the marks come from that. I'm assuming the marks are going to be for the deltas 1, curly arrow, and create reagent with charge on a lone pair. Don't know. It's interesting. Fascinating. Next. Explain why 1-bromobutane it's much less soluble in water than butane 1-ol. A detailed description of the forces involved is not required. 1-bromobutane has dipole attractions between molecules. Water has hydrogen bonding. Hydrogen bonds between the molecules. Hydrogen bonds much stronger than dipole attractions. It seems like an awful lot of words. Hydrogen, you've got to write all the words as well. You can't cheat. Hydrogen bonds much stronger. Stronger than dipole attractions. Not very soluble. Very soluble. Butane 1-ol. Butane 1-ol can form hydrogen bonds with water. Bonds with water. So much more soluble. Blimey, it's an awful lot for 3 marks, but fine. Section C, sorry about that, folks, didn't mention that. Section C is in mass spec, love it. Right, organic for ethanol, there's the last big peak, really great this. This paper highlights exactly what I was talking about in class year 12, which is there is a peak there at 47, but it's tiny. The reason for that peak will have been from a carbon-13 isotope. Yeah, but the last big peak is that one at 46, which makes total sense because that's ethanol. Yeah, there's the molecular ion peak. And it then says there's the infrared, there's some data. State what can be deduced about ethanol from the presence of the peak at 46. Can be deduced its relative molecular mass. Its relative, no, it's molecular mass. Would it be relative? Yeah, it still would be. Still has to be. Oh, sorry about that. Oh, have I left my face showing? I have. Been staring at my forehead at the side. Lol. 46 is its relative molecular mass. Parent peak. Identify the species responsible for peak at 31 in the mass spectrum. Right, this now becomes a lot more tricky. Right, let's just draw out ethanol. Yeah. There are certain bits in mass spec you should always learn. Yeah. So number one is that's the parent peak when it's plus charged. But then what we can do is we can chop it. If I chop it here, that there is 15. Yeah. CH3 plus is 15. CH3, CH2, you do get used to these, is 29. Yeah, that's 29 peak. That's to cut it here. Well, if the total thing is 46, if I do 46 minus 15, 46 minus 15, I get 31, don't I? 31. So what the rest of it, that there is going to be the peak responsible for the 31. So identify the species. So I'm just going to draw this out to make this easy so you guys understand what I'm doing. Yeah. So this is ethanol at 46. Yeah, we are going to split it here. This tail piece here is 15. Not going to see that. We want the peak at 31. Yeah, so this piece I'm actually going to draw out COH. I'm actually going to draw this all out and put the plus charge on the C, as that's who owns it. And that has a peak of 31. And state how it's formed. Fragmentation of the carbon-carbon bond. Fragmentation of carbon-carbon bond. I like it. Identify one feature of the infrared spectrum that confirms the functional group is an alcohol. Broad peak, that one right there. Yeah, broad peak at 3,100 to 3,500. It's probably going to be here, isn't it? There you go. Yeah, absolutely, makes total sense. So I just want to quote that data right there. It has a broad peak. Yeah. The IR spectrum has a broad peak, broad absorbance. It's actually trough technically. A broad trough at it. What do they say? They have broad absorption. Yeah. Bond stretching vibrations. Has a broad absorption at 3,200 to 3,750. We're done. Chemical tests are often used for identical organic groups and molecules. Explain the meaning of the term functional group. The part of a molecule that gives it its don't like that bad English. The part of a molecule that gives the substance its chemical properties. Want to see, that's the first time I want to see the mark scheme. Now I want to see it. Very interesting how it's taken me that long before I'm like, oh, okay, now I want to see that. Yeah, IAL papers, AS, paper 2. Right, well, we've been doing question 23. Definitely want to see those words for this. Absolutely, 23, there it is. So I can check all the rest of them. Yeah, mixture goes darker because concentration increases. Mixture then turns paler on standing because the equilibrium shifts to the right. Happy with that. Oh, blimey. Yeah. Right-hand side has fewer molecules. Left-hand side, more molecules. I miss M3. You see, this is always worthwhile adding in those little bits. Yeah. Hang on a minute. Oh, pressure. Did I talk about temperature? Oh, no, hang on. So there you go. I missed this one because this is gases. I ran out of space. That's why, because I was drawing diagrams. Yeah. So I'll put in red. Of course it is. Yeah. 2 moles on left, 1 mole on right. One mole on right. It was about pressure and gases. I should have mentioned sides. Should have done it. Yeah, this one's all okay, I think. This is where I think it actually becomes really useful if I split my screen. I think I can do that. That one and that one. There we go. 2A, equilibrium shifts left. Endothermic reaction. I like it. It's fine. Alkali reacts, removes H+. Oh, they allow the equation increase amount of, nope. Equilibrium shifts to right, forming yellow. Yeah, equilibrium shifts to the right. Yeah, well done. All okay. Oh, I was a little curious about the mechanism. Reagent, sodium hydroxide, conditions, aqueous water, and heat. Oh, allow warm. There we go. Yeah, it needs to be warm. Better. Mechanism. First curly arrow is M1. Second curly arrow from CR, M3. Dipole, M, correct organic product. What? It said from, you do not. That's naughty of Excel, folks. I should have drawn it. I did think about it. I did. Don't see why they're making you draw it, though. Shouldn't have to do that, folks. Shouldn't have to do it. It's not part of a mechanism. That there is a fault with Excel. They asked for the mechanism. The mechanism does not include the product. That there is the mechanism. Yeah, and then I'll put BR minus over there. There we go. But anyway, fine. I'll do it for next time. Next. B. Water forms 2 hydrogen bonds. Ugh. Needing the word to any 3 from. Blimey. Butane 1-ol forms hydrogen bonds. Yeah, hydrogen bonds. Hydrogen bonds. Butane 1-ol can form hydrogen bonds with water. Hydrogen bonds with water. There you go. Butane forms. Yeah, 1 bromo. Are there ignore dipole interactions? Huh? How bizarre. How strange. That makes no sense. Huh. I don't get it, folks. Why are they doing that? Dunno. Cannot form hydrogen, but has water bonds are stronger. I'll bear that one in mind. Red. Yeah. So we want to be saying, has Lund, that's so untrue. That's not true. It is DDs. Don't care what anyone says. That's a dipole attraction. How bizarre. I'd want to ask. And then one does and one doesn't. Fine. Nasty question. Horrible. Molecular mass. Yep, I like it. 46 is its relative molecular mass. Reference, ignore reference. Yeah, molar mass. Molecular ion, MR. Yep, fine, good. Section, good. Lost CC bond is broken. Ignore fragmentation. Interesting. Okay, yeah, cool. So it has a broad spectrum in it. Yeah. Functional group. Group of atoms, part of a molecule. There you go. Part of a molecule that determines its chemical properties. I like it. Cool. Let's get rid of that. Let's go full screen again on that one. All right. The reaction of sodium metal. Change my pen to black. Reaction of sodium metal with ethanol can be used to confirm the presence of the functional group of ethanol. Give the equation for the reaction. Yeah, do you know what? Very interesting, this. Now, it says give the equation. State symbols not required. I'll go for structural since they've given me a huge amount of space, mind. Yeah, they're saying that I can do this as displayed if I really want to. It's very odd. Very odd. Very odd. Oh. There we go. Balance of the half. That's liquid, technically. Solid, aqueous, gas. Next. Carboxylic, by the way, I don't like one of the things with that, by the way, just to let you know, I don't really like doing that. Yeah, what I prefer to do is to do that. That's better. Better chemistry. It's ionic, you see. Yeah, rather than being covalent. I like that little extra bit of detail. Yeah, carboxylic acid E was investigated quantitative and qualitative. Ah, good old calculation. Calculate the mass of carbon present in sample E. A sample of 1.2 grams of E was burnt in excess oxygen. A mass of 1.79 grams of carbon dioxide was formed. How fascinating. So E, carboxylate was investigated. E was known to have one of the following structures. Okay. Give the mass of carbon present. So, okay, guys, if we take either one of these, because these are isomers of each other, we can go C, 1, 2, 3, 4, 5, H, 3, 5, 6, 7, 8, and then O2. No. Yes. Ooh, that's odd. Hang on, that's strange. Oh, then they're not isomers. I tell a lie. They're going to ask us to figure out exactly what's... Oh, this isn't... Okay. Plus oxygen goes to CO2 and water. What we realize, folks, here... H2O. Okay, this is technically combustion analysis. I don't think I've ever taught you this year 12. Well, the first thing we can do is we can always work out the moles of carbon dioxide. So number of moles is grams over rams. Yeah, we know this. So we've got 1.79 grams of CO2, which has a mass of 44.0. We get used to this after a while. 1.79 divided by 44 gives me 0.0407 moles of CO2. Right, well, the thing is, though, if we balance the equation, yeah, I don't really need to balance it entirely, but, you know, oxygen's 10, 14, it's 2 already there. If it's structure 1, this is S1. Yeah. So that's 10, 14, 2 already there, need 12, 6, there you go. But what we realize is, in order to get back, the sample of E was burned in excess oxygen. A mass of carbon dioxide would fall. Calculate the mass of carbon present in the sample of A. Okay, so ratio in the equation is a 1 to 5. Yeah, there's a 1 there and a 5 there. Let's underline it. 1 to 5 ratio. I'm going to write that down. Yeah, 1 to 5 ratio, and I'm going in that direction. So divide by 5. Divide that number by 5. Damn it. Just gone and lost that on my calculator because I pressed the wrong button. Divided by 44. Divide that number by 5 to get me down to 1. So I'm going to get 8.14 times 10 to the minus 3, but I'm keeping that on my calculator. That's moles of... Oh, hang on. Hang on. No, don't even need to do that. I'm wrong. I'm wrong. Right, so we know that this is the moles of carbon dioxide. Well, how many carbons are in each carbon dioxide? And that's 1. So that there is also the moles of carbon. Huh, clever. So just multiply it by 12. Huh, clever that. 1.79 over 44 gives me the real answer. Times that by 12 to get me back to carbon. And I get a mass of 0.488 grams of carbon. That's very clever, folks. Yeah? We realize that all the carbon in the carbon dioxide, that's actually the hardest one so far for understanding wise. We've calculated the number of molecules. I feel like I want to actually break this down a bit further. Yeah. We've got C, by the way, we don't actually know which one it is. Yeah. Plus O2 goes to CO2 and water. Right. If I've just been told that I've collected 1.79 grams of carbon dioxide, well, the great thing is in CO2, yeah, in one CO2, there is 1 carbon. Yeah, if I have 2 CO2s, I have 2 carbons. The number of atoms of carbon is the same as the number of molecules of CO2. So when I divided that by 44, I'm actually calculating the number, which was I can't remember what that was, 1.79 divided by 44. Yeah, 0.0407. Yeah, that is the number of molecules, or the number of moles of CO2. I can multiply by Avogadro's constant if I want to turn it into molecules. But if moles of CO2, well, that's going to be the same. CO2, 1 CO2 equals 1 carbon. So that's the same number. Yeah, so that is the moles of carbon. So then I've just got to multiply it by its relative atomic mass, which is what I did. Very clever. Yeah, that's sneaky, that. The mass of hydrogen present in the sample was 0.0610. Deduce the mass of oxygen in the sample. Oh, okay, well, that's quite nice, conservation of mass. So we've got carbon, we've got hydrogen, we've got oxygen. We've got carbon at 0.488, oxygen at 0.0610, and the oxygen's going to be the rest, and these are all grams. And the total thing weighed 1.2 grams, which is E. Right, so I can work out the rest. So I can do 1.2 minus 0.488 minus 0.0610, and I get an answer of 0.651 grams, and there's my answer. For 1 mark, that's all I need to show. Next, uses information to calculate the empirical formulae. Thought that was coming. Yeah. So turn the percent sign to a gram sign. It's already done. Yeah, it's already done for us. Divide them into moles. Divided by 12, divided by 1, divided by 16. My year 10s can now do this. They can now run the empirical formula properly. I'd love to show them that question, actually. Divided by 12 gives me 0.0407. This is 0.0610, and I've no idea what that's going to be. 0.651 divided by 16 has to be 0.0407. Look at that. Divide them all by the smallest. 1. Yeah, I won't do that. I'll be good. 0.0407 gives me 1. Shouldn't underline it. Don't like it. 1. 0.0407. Let's do that number. Put 0.0610. 0.0610 divided by 0.0407. Going to get a fraction 1.5. That one, of course, is the same number. So now we just double everything to get rid of that half. Times it all by 2. Final answer is C2H3O2. Right. Deduce the identity of E. Give a reason for your answer referring to the information at the start. Right. Clever. So what we're going to do is work out the empirical formula of these guys. I feel like I want to keep that on my thing. It's rather frustrating, to be fair, because I have to write tiny now. Yeah, so hang on a sec. I've already done the top one. The top one was C5H8O2. That's the top one. The bottom one is 1, 2, 3, 4, C4H1, 2, 3, 4, 5, 6, O4, C4H6O4, C4H6O4, and that's my correct one. So that one. Structure E is in fact structure number 2. Identify E. Structure 2. Structure 2 due to empirical formulae could be C2H3O2. There we go. Describe a qualitative test that would distinguish between structure 1 and structure 2. State the expected results. Oh, okay. It's nice to see a chemical test appearing. One's an alkene. You can't test for the carboxylic acid because one or the other one has it. So you have to test for the alkene there, folks. So you're going to use bromine water. Test bromine water. And number 1 will structure 1, orange to colorless. Orange to colorless. Number 2, no change. You can't put no observation. It means you did it blindfolded. Draw the displayed formula of the compound that can be oxidized to form structure 2. Okay, so that's butane dioic acid. Draw of a compound that can be butane. This is what it is. Yeah, that's what it is. Butane dioic acid. We need to turn it back. Yeah, we're going to reduce this because we need to form this on oxidation. And we know a primary ol will form an aldehyde on oxidation and then form an oic on oxidation. Right, we've got 2 choices. Either draw the diol or the dial Either one. I'll go for the diol. Why not? Here's the diol. There you go. Butane 1,4-diol. And it's displayed. We have to show every bond, every atom. Can't cheat. There you go. That would explain why a molecule of structure 1 can be shown geometrical isomerism. Structure 1 can geometrical from structure 1. Ah, it's got, okay, yeah, sorry, my bad. Structure 1 contains a carbon-carbon double bond. Carbon double bond, which cannot rotate, 1 mark, and each carbon is bonded to 2 different groups. Love to know what the mark scheme says there, exactly what they want to say. That one is of interest to me. Yeah, it all makes sense with all the answers following like that. Test bromine, yeah, fine. Diol, would they accept the diol? Huh, it's a bit wrong. Oh, any combination of aldehydes or alcohols or single carboxylic can be oxidized. Yeah, okay, that's fine. Restricted rotation, carbon-carbon double bond. Each bond is attached to 2 different groups. There we go. Happy with this? I think that brings us to the end of the paper, does it not? It does. Look at that. Great timing. Right. Guys, I will leave you be. I hope you found it useful. I'm going to start on the paper 3 now. Yeah, I'm going to start on the paper 3 for next lesson with my year 12s, and I will see you guys all very soon. Take care, guys. Have a good day.